So we're going to go into you might be able, and fourth hour is longer than third, so you might be able to take care of that. It depends too on how fast we go through this first part. Last hour was able to do this almost immediately, but I throw this topic, it says impossible integral in your, take out your calculator by the way, you need it for this and you need it for something we're going to be creeping up on in your notes, but last hour, most of them were able to get this without me saying much. So, but sometimes this type of integration throws people off. So I'm going to just make sure, there, now it's finally going full screen. So just take a minute, and I'm going to pause this so I'm not talking, but this one's usually hit or miss. What they're testing is, do you know the language of calculus? And then you can do it two ways. But like you said, Adam, when it's an antiderivative, it means it's the result after you have integrated the function, right? So what I get when I do the antiderivative of this is capital F of x. That's really what it means. This is a definite integral, right? What are the limits? 0 to 3. So you have to remember how you do an antiderivative. You would do from 0 to 3. This is the fundamental theorem of calculus disguised with some funky language. So this is actually the antiderivative evaluated at 3 minus the antiderivative evaluated at 0. That's what it means to be an antiderivative. It is the result after you have integrated. You don't have to integrate by hand because I said this would be calculator active. So our goal was to figure out what f of 3 is. It's a very easy entry on your calculator, right? Because what will you do with the f of 0? You'd add it on. Yeah, you'd say, well, I'm just going to add that on, which is really going to just do a 2 plus. And this can all be done on your calculator. And what is it? 2 point. Awesome. Now, last year I taught this two ways. Last year we talked about this too, as if you want to consider it as being accumulation, that this is a rate of change and this is an amount. We said, well, you would start at 0, you already had 2, plus this gives you, we talked about it with snowfall, this gives you how much you've accumulated from 0 to 3 after starting at 2. So you can think of it with accumulation, but the intent is that you understand what an antiderivative is, and then use the fundamental theorems. We're going to try one other one. Be careful of your limits on one like this. So when it says f of x is an antiderivative, you have to say, well, when I integrate it, I get capital F. That's what that means to be an antiderivative. This you can't do right now. It's one, usually they'll give you one that's not possible to do by hand, and you'll waste time when it's calculator active. My limits are what on this one? Yeah, make sure you go build up in order so you don't have it backwards. It'd go left to right. Otherwise, if you're going to go the other way, be careful, right? So I'd go from -2 up to 1. This would go from -2 up to -1. So this one's going to have a little bit different presentation because I'm going to put the top in. And again, they're giving negatives in here because I think they want to avoid that whole accumulation process. The intent is you understand that this is an antiderivative and then use the fundamental theorem of calculus to subtract at the top minus subtract at the bottom. The reason I said be careful on this one is because it's asking you for this guy. Yeah, so it's asking for the f of -2, so you'd have to add that over to the left-hand side and then subtract this from. So you would actually, to get f of, you'd have to take 2 minus the integral to get your f of -2. So adding that to the left and subtracting from the right. And I know you know how to work your calculators. I just discuss this every time because this one will get you and it's an AB one. So one more of those and then we'll move on for today. Let's just do this guy. Not one that's even possible to antiderivate by methods learned yet in class, and it's not intended. The intent is you go use your calculator. So let's try that guy and then we'll take some notes. Be careful whether you're going forward or backwards if you're using that accumulation model. We haven't been on our calculator hardly at all this year. So I'm missing Sparky and We didn't do this one last hour, so I don't know the right answer. So if somebody wants to offer it up, what do you have? Is that a backer on that? Yep, two of you, 18.447. Can you, are you guys good? All right, super. Then we don't need to do any more. I just do as many as you need. So our last topic is improper integrals. This section gets really tricky. This is kind of Calc 2, like one of the hearts of it. Improper integrals are a big Calc 2 topic. Series and polar parametric, they're kind of our big new things. We'll spend 2 to 3 days on this, then we'll be done and prep for a test. So what happens with an improper integral, unlike what happened in AB, is one of two things. Either a top, and I can put any number down here, it doesn't matter, or I could even put a negative infinity, but this kind is really easy to spot. When you see an infinite bound, you know you're dealing with an improper integral. How we deal with it, you got to be careful. So that would be called an improper, or if I went negative infinity to 5 of some function, this is also called an improper integral. When one of the bounds, upper or lower or both, you're going to do one in the notes where it goes from negative infinity to positive infinity, and they're easy to spot if you see the infinite bounds. You can just see it. The trickier part is now, unlike in AB, this is easier for me just to show you without the variables. If the integrand has a discontinuity, in particular a vertical asymptote, so go ahead and write that, at some place at least once, at or between the limits. So I'm going to put a couple up here that fall under this criteria. I'm just going to go from 2 to 5, and then let's just do maybe 6 over x minus 3. Prior to today, you wouldn't have been on the watch for this, and you would have just done an antiderivative. You would do 6 ln, right? X minus 3 and plug them in. But this one has a discontinuity between your limits of integration. Where is it? And you're being asked to hop an asymptote. Somebody last hour said, what does my calculator do for that? And I've seen different things with different calculators. Last hour, somebody said, can't do it, can't divide by 0. Somebody's actually tried to do it and got a number. So the different calculators are different, but there's a big issue here at 3. Graphically, there's an asymptote. We're going to have to deal with it. All right? What does your calculator say? You're trying it right now. What does it say? See, answer, something about accuracy, a warning. They are all programmed differently. And so that, but the key to it is note it. It's actually kind of, what does yours say, Adam? It's just giving you the worm. So, yeah. Yikes. All right, are we back? So that kind of proves my point. And when you try to hop an asymptote mathematically, different things happen. So what will happen on the AP test if it's multiple choice? If you don't recognize that this is an improper integral and just do it as normal, maybe you get 7, and 7 will be there because they'll anticipate it. So it leads you to a false answer, and the calculators all deal with it differently. We're going to have to figure out how to deal with it. The notation is messy. Here's another one. If I went from 0 to 6 on this guy, this is one where it's at least one value of x between the limits of integration or on them. It says at or between. This is at. So this is also an improper integral because there's an asymptote at one of the limits. So at or between, you have to be on the lookout now. There's always one multiple choice, and I will put one on your test. And if you miss it, you're going to get a false solution. So now when you guys are evaluating, you always need to look at your limits and make sure there's not a discontinuity. If there is, there's a whole different process. Well, it's linked to what you know how to do. So most of my notes today are for you to understand sort of the procedural part of it. We're not going to do any full examples, but I'm going to have you get some theory down. If I taught this in a one-semester course at a college, I'd probably cut out today and just say, this is how you do it, memorize it, and you'd be fine. But I like, when I have time, I like to build in like some theory behind it. So we're going to build to it. Here's what I want you to do. We're going to go graph this guy. This guy's the volcano graph. 1 over x squared. And we're going to talk in general about 1 over x to the p for a while. But here's 1 over x squared. And we're going to be integrating from 1 on out to infinity. So I'm really asking you graphically for the area of this stuff that's going to accumulate forever. So your gut reaction would to say there's an infinite amount of area under the curve. Sometimes there is, sometimes there isn't. For this specific case, actually, this does have a finite answer to it. There's a finite amount of area under here. It seems weird. It messes with your head. So this is where on your calculator, we're going to kind of show it and then prove it. So we're going to go by row. Melis's row, I'm just going to have you creep up and just go to 9. So you're just going to go 1 to 9. Next row, just math 9 that. Elizabeth's row, go ahead and let's go farther on out to infinity and do 1 over 99. Just to see what's happening when I start walking towards infinity. I'm actually doing a limit. TJ, if you could do your row, do 999. If your calculator's not working, Savannah, if you could back that up. And then Joe's row, do this. Some of the calculators, again, it depends on the calculator, showed a error with this one. It said something about, we'll see if one of you has those calculators from last hour. I think that's far enough. So you're going to see what happens with this one versus the next one we try to creep up on. Just from 1 to 9, how much area accumulated, Melis? 0.889. All right, that doesn't lead me to any conclusions, right? The next one, Bethy, what did this guy? 0.989. All right, next one, 998. We'll leave it. And then what was yours? Did yours calculator handle it? Because last hour, a couple of them couldn't deal with this big upper bound. What was yours? Point? Yours is still 9998. All right. So do you see now? If I were to now, if I had like a better calculator, a TI-89, it would allow me to put an infinity in there. Ours don't. But what do you think the answer actually is based 1? All right. I mean, I'm not 100% sure. I will be in a little bit when I do it with analytics, but graphically, it seems like it's settling at 1, but it's all about it being a limit problem. And I had you guys creep and do a limit. I said, let's go from 1 up to, and I kept changing that upper limit. I said 9 in this row, 99, 999. We were actually doing a limit. I was having B approach what? Infinity, and I didn't get very far. I would need an infinite amount of rows. Right? But I got far enough where you could already see that the graph of this, or the area it was accumulating, seemed to be settling at 1. That's a conjecture. I'm not sure, but it sure looked like it did. When that happens, we say that the integral converges. And when we get to our series, when that happens, we'll say that the series converges. If we couldn't grab it, like the next one I'm going to do, I'm going to ask you to go by rows, and we're going to have a hard time grasping the number, then we say it diverges. All right, so we're going to have 2 things, converges, and if so, to what? And then diverges, which means an infinite amount. So we're going to go take a look and see if we can do this one without just guessing at it. This is the correct notation that you have to show on the AP exam. And I'll show you as last year's I brought up just so I could tell them, see, this is how it's graded. They say that you have to, on an FRQ, you cannot treat infinity as a number because it's not. If I said to Adam, plug infinity on your calculator, the best he could do is 9999999 until he croaks over and dies, and then he's done. But he didn't get there, right? So you have to creep up on infinity as your upper bound. You can't use it for, again, I'll give you when we get to multiple choice a little shorter way to do it, but you must pass off to the limit or you'll lose a point, if not 2, on an FRQ, and it's a common FRQ part. So anyway, this is how you start, and it's exactly what I told you guys to do by row. I said, let's keep changing that B. You integrate this as normal. Now this one's easy, but once we get into some of the examples tomorrow and even today, of the 4 you have to watch on video, 1 goes by parts. 1 in here goes arctan. So you have to know all your integration techniques, and there's even some L'Hopital's rule because you're doing a limit. So everything kind of combines in one big section. We're going to start easy though, because this antiderivative is easy, right? What's the antiderivative of x to the negative second? Negative 1 over x. We still hang on to that limit notation until the variable is gone. The variable in this case is x, right? B is a number that's going into the top limit. So you still are going to say the limit as B approaches infinity, you do plug in B. It's kind of a long way to show it, but you have to. It's not proper math to treat infinity as a number. It doesn't work as numbers do. If I said, what's infinity minus infinity, what's your answer? I don't know. Exactly. Keep that in mind, by the way, when I show you last year's FRQ. They got a doozy for this process, which sometimes I can predict, and I kind of usually think they're going to be easy. Last year, they had a pretty tricky one. Anyway, so now when I send B to infinity, what is this going to for sure? This is 0, and I get minus a negative 1. So I've now actually shown, we crept up on it, and we were pretty, like TJ said, it's uno. It was looking very much like 1. This is showing it's exactly 1. So because it was at 1, we say it converged. Had we been left with infinity, now keep in mind, it could have been infinity plus or minus any constant, and what's the answer? Infinity. If you have infinity minus infinity, we don't know. All right, so be careful with how we answer them when we say it diverges. But let's go hit diverges over here, and let's go to the next page. So this is what I just told you. That's just a screenshot off the internet. I'm gonna go over here. First thing is recognizing whether they're improper or not. On your test, they're not all improper by any means. But you know, if there's 20 of them, maybe 3 or 4, because it's one of our bigger topics, would this guy be considered improper? No, you can even just do it in your head. This one's easy to spot because of the infinite upper bound. So that's easy to spot. The next guy, improper or not? Yes, because of the asymptote at the definite, the limit of integration. This one, definitely, and this is the kind I'm going to caution you about for multiple choice, because you're going to look at this, you're going to go natural log, hopefully you're going to go, well, there needs to be a 1/2 fraction correction, and you're going to go about your merry way trying to solve this. Meanwhile, you hopped an asymptote, which is not legal when accumulating area. You can't just jump over an asymptote. So this guy requires different techniques, all right? There's an asymptote at 3/2, which is between my limits. Do you get how do you spot them? This guy for sure, improper. Why? Infinite bound. Awesome. So let's move on. So this is where it gets kind of interesting. And really listen, because if you get the theory, it'll not only make this section easier, but it'll make our whole series chapter easier. All right, the whole theory of diverging and converging. So this guy is almost the one we just did. Remember, we did this guy, and we did it on the calculator. We were creepers, and then I actually proved it, but we said year 1. So go ahead and put that over. I'm giving you almost the same graph. And if I leave the axes unticked and I stay in the first quadrant, it almost looks like it's the same graph, but it has a very different result. And I want you to understand why. I am still accumulating what seems to be an infinite amount of area. Agreed? Watch what happens, though, with this one. On the calculator, we're going to go through again. We're going to do the exact same thing with the rows. We're going to go to 999, 999, and hopefully that last row, second to last. Go ahead and watch and enter them, and I'll just read it off the first person's calculator. The last one, it went 0.89, 0.98, 0.998, 0.999,899, which was like, okay, this is 1. This guy, when I'm doing the exact same creeper, it looks like it's starting at 2.2. I'm going to round to the tenths. 2.2, then 4.6. I totally have I can't grab a hold of the answer yet. That made a pretty big leap. And then to almost 7, right? So it went 2 to 4 something to almost 7 to 9 to, did anyone try it over here with a bunch of 9s? Yeah. Anyone, 5, 9, we couldn't, what happens is I can't definitively tell you that this area is settling, and it's because it's not. What do you think the answer to this one actually is? Infinite and it diverges. Now I'll show you with the analytics. This is how you have to be able to show that, and then I'll tell you, this is a very special one, by the way, up here. If you can keep him in mind, it's going to save you a lot of work. But I remember we can't actually use infinity. I couldn't say, hey, Adam, put infinity in. All I could do was get as close as possible. We replace that with a b. We say b is approaching infinity. And we do 1 over x dx, and we antiderivate as normal. You're just not allowed to drop that limit, right? So what is the antiderivative of this? Yes, and I'm keeping the antiderivatives nice and easy right now because I just want you to see some theory. So this would, again, I'm not going to drop that limit yet. I still have the variable in my expression. So this will be ln b minus ln 1. So as b goes to infinity, what does natural log go to? It goes slowly, but it goes there. So this is infinity minus, and what's natural log of 1? 0, and that could have been minus a billion. And what's my answer still? Infinity. Be careful, though, because on last year's, it ended up being this. And I'll show you how it was dealt with. I have it open in the back. I have a tab open so you can see last year's went very tricky in that their integrand required decomp before they could even integrate it. They had to know how to do partial fraction. And then it went harder. All right, so wait, back to this guy though. So this guy diverged, right? And 1 over x squared converged. I want you to see how I would have graphed 1 over x squared on the same axes. They'd still go through 1, 1. But watch this. This guy would be at a half at 2. That's 2 comma a half. If it was x squared, it would have been down at a fourth. Do you see how it's going to the x-axis faster, right? And at 3, this guy would be up at 1/3. The other squared one would have been at 1/9. And so what happens is it ends up going faster to the x-axis and fast enough, the x squared one, where it settles. This guy right here, 1 over x, I like to call the fence for divergence. What did I just say I like to call it? Fence for divergence. Yeah, anything above it. If this guy diverges, has an infinite amount of area, and I'm above it, won't it also diverge? Like, that's a big concept. But if you're above a divergent, you must diverge, right? This guy's the fence. So anything 1 over x to the p that will ride above this guy will diverge. If it rides below it, guess what happens? Yes, that's why we call him the fence. It's going to allow you to take some shortcuts. We're going to creep up on it. So let's talk about this one. Just theoretically, I'm going to go put my fence for divergence on here. This is 1 over x. I just want you to see what happens. This is y equals 1 over x. And I'm going from 1 on out to infinity, and we just saw that did not accumulate a convergent amount of area. It diverged. Watch what happens with 1 over root x. Let's say at 4, 1 over x would have been at 1/4. Where would 1 over root x have been? Up at a half. Do you see how it would have been above it? What do you think my answer is going to be for this? Infinite amount. Yeah, or divergent. Now I'm going to show it to you with the work so you can see it. So we start as normal. I'm getting somewhere with this, by the way. I really want to save you a ton of time after I get through the theory of it. And I feel like you're getting it, which is cool because this is actually very abstract math right now. So I take that limit. Right, I go from 1 to b, and it was x to the negative 1/2 dx. Procedurally, you antiderivate that part as you always have. Might be by parts, might be partial decomp like they had last year, might be inverse trig, but this one's easy. It's just x to the 1/2 root x divided by 1/2. There's the antiderivative. Don't drop your limit or you're going to lose notation points. And we're going from 1 to b. Are you with me? Am I going too fast? Kara, am I good? You guys are way back there. Ashley, am I good? Can you see? All right. So I don't drop my limit yet. There's still, my x is still in the expression. I'll get 2 root b minus 2 root 1. What happens to 2 root infinity? Where does it go? Infinity. And remove 2, where am I? I'm still at infinity. correct? What do you guess this neighboring one's going to do when it's the 1/3? It's going to diverge as well with a similar process. Now I'm going to go to the other end of it. This guy, we already did it. We said it converged to 1. We want to come up with a pattern. Try not to blurt it, because last year somebody blurted it after, and I was like, oh, wait. They're like, I see it, it's and I was like, oh, wait. Let us think about it. All right, so there is a pattern for these, so you shouldn't have to show the work if you understand where it comes from. So let's go put 1/x² on here. We already said that this collapses to the x-axis fast enough to settle. 1/x did not. It rode above it, and it diverged. But this guy settled at 1. Are we good with that? So let's go see what this guy, and I'm going to throw out good notation just for speed. So I am going to treat infinity as a number, and any formal mathematician is going to roll over in their grave. All right, but we're going to do it just to ease up the workload. 1/x³ still has this bullet point like this one did. Will it go to the x-axis faster or slower? Faster. Exactly. See, you're getting the theory behind it. It's going to ride under one that I already know converges. So what do you think I'm going to do? Converge. It's to what that now I'm concerned about, right? It will go to the x-axis faster than one that I already know had a finite amount of area. It's a very high thought process here. Let's go do it with sloppy notation. I'm going to treat infinity as a number. I'm going to call that x to the -3rd dx. I'm dropping limit notation right now. Don't you do it unless it's multiple choice. All right, this would be x to the -2 over -2. I'm dropping all my good notation. It's just for showing you how it works. This is what I actually have going for the antiderivative, right? And then I'm going from 1 to infinity. The upper bound goes in first. What will that give me when I do 1/2 times infinity squared? And that really makes me cringe because I can't square infinity, but I'm doing it. All right, 0 minus -1/2. Agreed? This converges and it will settle. If I told you guys to creep using all your 9s, we'd end up with 0.49, 0.499, 0.4999. We'd be able to grab it at 1/2. All right, go do the next one similarly to this. All right, and see what you get. It's going to fall out almost identical to this one. That would have been x to the -3rd over -3. Right? So do some sloppy work, and it is slop. I know it converges. It's going to go to the x-axis even faster than the other two. It'll converge to something less because it's going to have less accumulated area. What do we get? All right, so now let's see if we can get a conjecture here about how maybe you could just do the 1/x to the p, which, by the way, is a really common question, just in general for any p-value. What do you think that one is? 1/6. So what do you think the formula is? There it is. But I don't like to just tell you because I like you to have a proof behind it. So if you're not a proof person, you nod and smile and just memorize it. If you like to know where stuff comes from, this is kind of how you show it. So a conjecture is something that seems to be true based on observation. Once you can prove it, it becomes a theorem. That's the difference, okay? So my conjecture is this, that when I integrate from a constant up to infinity, I could put a 2 or a 3, it doesn't really matter, 1/x to the p dx, my conjecture is actually twofold. Let's call it a piecewise conjecture. Boy, that sounds good. We're going to do it piecewise. Yeah, I felt really smart saying that. I don't know if it's a thing, but it's a piecewise conjecture. What am I saying? I called 1/x to the first the fence for divergence, and anything under that, like x to the 1/2, x to the 1/3, those diverged as well. So when p, sorry, that should be a p. So when p is less than or equal to 1, this would imply that we diverge. I'm not going to prove that part because we just kind of showed it. The trick is when p is greater than 1, we know we have converges, but we actually, you guys just said what it converges to because you saw it happening. What'd you guys say? 1/p minus 1. Why is that? And could it be shown? And the answer is yes. And once I'm done showing you, we're done. I'm not going to do the examples. So here's how it goes. I'm going to, again, it just has a lot of variables in it, so I'll slow down a little bit. I actually think when kids come back or talk to me or email me after graduating, the ones that go on to higher levels of math, they often say the things that were the most helpful was this proofy kind of stuff. Because it, I don't know, it just makes you understand it a little better, I think. But let's go take a look. Boom. Nobody ever says, gee, Luru, thanks for doing USub. Well, everybody does USub, right? But sometimes these proofs, if you understand them, they're one of the more helpful things we do. So we are going to go just generically integrate this for any p. So this would become that integrand. And we're just going to go through and see what happens. My proof is going to be 90% solid. I'm going to take a couple little liberties with it, but we'll be good. So when I integrate just in general, what do you do with the exponent? Add 1, divide by it. So it's going to become x to the negative p plus 1, and I'm going to divide by it. Good so far? Oh, yeah, thanks. What am I doing? Yes. Sorry, I did the antiderivative. I have bad notation here. Then what I'm going to do, just because I don't like negative p plus 1, I like 1 minus p. So I'm just going to do that to make it look better. I'm going to give a little facelift before I keep going here. I'm going to call it x to the 1 minus p over 1 minus p. So that's just a facelift, right? Then I'll use the fundamental theorem to deal with this piece of it. What am I going to put in first? For what? X, not the p. Like, that means you understand it. You're not just replacing rando variables. P would be a constant in this situation. It's like 1 over x to the 8th or 9th or 10th. It's x that's the variable. So we will do the limit as b approaches infinity of b to the 1 minus p over 1 minus p. We good so far? Just a replacement. Minus, because that's what the fundamental theorem says. A 1's now going to go in for what? And what's 1 to any power? Awesome. So this would be a 1 over 1 minus p. Here's where the kicker comes in, and I'm going to kind of cut out a little notation that would probably be necessary. Are you all right with that? Remember, we're showing that when p is greater than 1, that's what this is. We're doing the convergent aspect of it. If p is greater than 1, I want you to focus on what happens right in the blue box. It becomes b to what kind of a power? Negative. Where do negative powers go? To the bottom as positive. I guess if I were to rewrite it, I'd write it as b to the absolute value of 1 minus p, which would be a positive power on the bottom. What would be on the top? Once I send the b's down, 1, right? Because if it maybe it was p was a 7 and that was b to the negative 6, it's going to go to the bottom as b to the 6. I just don't want to write it as b to the absolute value. Do you see what? I'm going to just jump over that little bit, but I want you to see that this is 1 over b, which is going to infinity, to a power, right? So what's going to happen to this whole piece of it right here? It is. That's going to go, and that's where I just skirted maybe 2 steps of the proof, but we could write them if we had to, right? So that's going to 0, and now this guy doesn't affect anything. I've got negative 1 over 1 minus p, but if I put the negative down here on the bottom and distribute it in, it's p minus 1. All right, so are you allowed to use that 100% if it's multiple choice? So if you were to see this on the AP test, right, and it's multiple choice, that's x to the 1/3, right? It's less than 1, right? So what does that do? Diverges. Yes, and that's what you would circle. Why show all the work? Because we just proved it. If this was to the 11th, you'd say, oh man, that's going to shoot down to the x-axis very fast. It's totally going to have a finite amount of area. In particular, it'd be 1 over 10 done. So there's power to doing that if you prove it. I don't like to tell you that stuff without showing you why. So on the next page, this is where your notes start. And you have, we're going to just do this one together. This is, by the way, just if you're listening, Your assignment is to watch the video notes on the next 4 examples. The first one, you should know the answer. We'll just take care of that right now. And then there's a 5-question video quiz, but don't have it open because I think I have the timer set on it for 2 or 3 minutes. So that's all you need to do for me by tomorrow. The answers build. This you should know right now. If this is multiple choice, what's the answer? Diverges, or you could say it's an infinite amount of area diverges, but if you had to use the limit process to show it, go do that for me really quickly, just to make sure you can. And again, this is only for 1 to x to the p. The other 3 examples I really start to mess with. You have to watch them. I just wasn't sure how much time I'd have today, so go show that one. We already did it, but just see if you have that notation that you need to show. I'll do it really slow. I don't care. I know what it is. I just want to make sure you know how to show it this way, and I'm going to show you why. I'm going to show you last year's piece of an FRQ. Yep, I want you to make sure you can show this when necessary. If it's multiple choice, you have at that. Yeah, I totally bet. Yeah, don't watch me. Divergent in math means doesn't settle. It's going to infinity. It can go at different speeds. For example, 1 over the square root of x diverges faster than 1 over x, but they both cannot be, they don't settle at a finite amount. So that one we did was growing really slowly, like you guys had 2.4 and then 4.6 and then 7-ish and then 9 and then 11, and we were already out to 9,999 and we'd only accumulated 11. But it's not settling, so we say it's divergent. Does that make sense? That's a good question for our series stuff. But this is how you should have shown this. Are you okay with that? Before I leave you for the day, you're going to see an example 2 that this guy becomes harder to integrate. How are you going to integrate that guy? That's a by parts. Then in example 3, how do you integrate the natural log of x? You either have it memorized or it too goes by parts. But this is different because how do we deal with the issue being at one of the limits? I didn't talk about that, so you need to watch how you show that work. Same here. How do you integrate this guy? That's arctan, but how do you deal with 2 infinite limits? So the notes are short, but they talk about some very important things. Last up, I want to show you last year's, and then you guys can just sit and chat. I think it was last year's, might be 2017. Scoring guidelines. Take a look. So look up here. This was the one that they had to do. But you know how to do it all. Their f of x was this, correct? That is totally not set up for U sub. It's totally not set up for long division because the degree on that, you have to run through all of your stuff. It's not a by parts worthy. It's not inverse trig-y, I don't think, unless I tried to complete the square, but the bottom factored. So what's it going to go to? When the bottom factors, what is this process? That's partial decomp. You've learned that. Here's what happened, though, and what threw them off last year. This went to, as it normally does, it went to subtraction, and at direct input, the kids got infinity right here, minus infinity. And I remember them coming back and saying, did you guys get 0 for that one, or did you write diverges? And then some people were like, no, I got a weird natural log, and they were discussing it. You know how you guys do that? This was when they came back discussing what to do with this. And somebody who got an actual convergent one said, well, you had to make it a quotient. To get, remember, we have to make it infinity over infinity or 0 over 0. It's technically L'Hopital's rule, but you don't really need it for this. Because what does this go to? Well, it's infinity over infinity. That goes to 2. So this was the answer. So it went weird. on them. And so, but by the way, kids who didn't use or hadn't been taught to use limits, I think you had to forfeit the answer and the limit expression, because you usually once it kind of spirals down. So they didn't want you just treating infinity as a number, not doing a limit process. So that kind of got them. But what you gonna do, right? I'm done. I'm gonna turn this off. So your assignment is to do what?